Okay, so today what we are going to discuss is about waves now. And I would say it's continuation of fun. So what we learned last time was like, okay, we talked so much about the simple harmonic, right? And I would say that's pretty much like the whole infrastructure of simple harmonic motion. So you pretty much understand how you started from Newton's law, and then you get to the differential equation. You solve those differential equations to get to the solution. And it turns out by the form of the equation that you obtained from Newton's law, you automatically get the second order differential equation that has the solution in the form of sine and cosine. Okay, and once you have sine and cosine as your mathematical description of your motion, is automatically called simple harmonic, right? The reason it's simple because it's a single frequency oscillation. Okay, something just go up and down, up and down, up and down with a fixed frequency. So that's why. Now, we're going to get more stuff done here today. So once you have that thing going on, we are going to learn something extra from that. And it turns out this is something that happens everywhere. This is due to the interaction of, can I say everything? Right? It's the interaction of everything. When you do something at one particular position, it has some influence on somewhere around it, or I mean, even far away, as long as there are some interactions going on. And then you can imagine interactions could be gravitational interaction, it could be electrical interaction, magnetic interactions, or even like physical interactions. Okay, you can like have some spring, string, you holding hands, you lean on something, you push stuff, you pull stuff. So everything is just connected, right? So when things are connected, then there is something that we call waves. And what is waves actually? So it turns out what you are looking at is, let's think about it. Like if you sort of drop a rock in a pond or in a pool or something, then you are disturbing the water surface, or actually the whole water right there. So the water gets disturbed or gets, moved or gets, pushed or pulled, whatever, by having a rock dropping down onto it. And once you get disturbed, now everyone's sort of like, okay, then you're going to create a ripple. Okay. And that ripple is that due to in the area of the rock that interacting with the water over here, but the water here actually get connected to the neighboring molecules of water, for example. So when these things start to move, then eventually the next portion of the water will feel that move, and then will start to move as well. And then when the position next to that gets moved, the one next to it will move. Okay. And when that happens, then the one next to it will feel that, and then eventually it's going to move. And then once this thing moves, then the next one will feel that move, then it's going to move along with it on and on and on. And that propagation of this whole thing, that is the wave. Does that make sense? Okay. So that's why I'm saying the key that these waves is going to get generated is you need the interaction right here, right? Because if there's no interactions between the original whatever movements and the neighboring locations, then nothing happens. Okay, sounds good. All right, so that's why I can give like a quick, like a one sentence conclusion of what is wave. You can say, yeah, it's the propagation of disturbance. So the position that the rock dropped into the water, that is you creating a disturbance, and that disturbance get propagated out, and that propagation out, that is the wave. Sounds good? All right, so now you can imagine that that's how you create any waves. First, you need a source of disturbance, but sometimes the word disturbance may be disturbing you. It doesn't have to be disturbing. I mean, you create something, movement, you create some movement, something is moving. It doesn't get disturbed all the time. But I mean, all right. But anyway, that's the point. The point is there is some origin of movements going on. All right. And that movement supposed to be happens inside some medium. The example that I just showed you, there was just water. And then the key is you need some mechanism that adjacent portion of the medium can influence each other. And that's the interaction that I was talking about. Sounds good? All right. So that's pretty much like these are the three components that you need to create waves. Cool. Now, here comes the question. All right. So if we just want to talk about, classification of waves, there are one way that we can look at this one by looking at how the medium is traveling or moving. And this one is a complication that get into our business today. All right. Look at this one carefully. Okay. First, you have a spring. This is a spring. Even though for this particular scenario, you can use any string or rope or anything that will do too. But the reason that the textbook picked the string because we are going to contrast with another kind of wave down here, which spring can pretty much contain both types of waves. All right. All right. So up here, you have a spring. And now on the left end of the spring, there's a guy hand holding it. The right side, let's say it's attached to a wall or whatever is fixed. And then this dude over here just move his hands up and down. Okay. So of course his hands will interact with the spring, definitely. So when his hands moved up, then the spring will just get dragged up as well. So it will just start to move up along with it. And then eventually that moving up manner will get propagated over time. So that's what happens with this is you propagating that disturbance right here. Soon after this, then the spring will start to move up at the later position, and then next and next, on and on. Does that make sense? So that means right now you have something traveling to your right. We call this a wave speed. Let me put V on it. Okay, so now you have you can say velocity if you want to associate the direction to it. But let's say now wave is traveling with some speed. Cool. But then the thing is, your hands actually move in the vertical direction, right? So you're moving up or you're moving down in the vertical direction. So over here, you can see that now the direction of the wave traveling and the direction of the medium that is moving, because your hands moving up and down, then this medium also move up and down. Does that make sense? Yeah, it's only up and down here and up and down everywhere. Everywhere just go up and down, up and down. So every time that you have the medium traveling in the perpendicular direction to the wave speed or the direction of the propagation V, we call this a transverse wave. So the medium moves perpendicular to the wave propagation. Does that make sense?
Okay.
Okay. And now you can think in the opposite way, because now we have a spring. Instead of moving your hand up and down, you can move your hand in and out, okay, forward and backward. So in this case, of course, once you compress the spring and then you release out the spring to decompress, but the compress, decompress, compress, decompress will eventually get propagated. So that will give you the propagation. Once again, I can just highlight that's a compression of the spring. It's get extended here, eventually come out there. Does that make sense? All right. So that compress, decompress, compress, decompress will start to move. And that will give you, once again, the direction of the wave traveling. So that's a propagation of waves. And then I can call this one V just like before. But then now your hands or this guy's hand is actually moving in the horizontal direction over here. So it's parallel to the direction of the wave propagation. We name this a longitudinal waves. Okay. So the naming is just here, just so we can communicate to each other. However, what about the mathematics? And this is a nice thing about this one. So if somehow you are able to identify the movement of the hands, and of course, you can guess what kind of movement are we going to get? Yeah, we are going to do the simple harmonic thing. If you want to generate something that is a sinusoidal waves, but that's, wait for it, right? It's just kind of like spoil here. Okay, but anyway, so what it's going on over here, you should be able to somehow describe this type of motion, the hands motion here. But then no matter what you do, you want to do it separate from the speed of the wave. So that's why you can call this subscript T. It's a transverse velocity, just to distinguish this one with the speed of the wave. So we have different V right now. There are two V's at this point, okay? Or this one you can call it maybe V sub L, or let's call V sub X, let's say. So this one is going to just identify that this is the medium, the elements of the medium that is actually gets to travel back and forth, back and forth, back and forth. Okay, cool. So this is where the complications set in, guys. We have two velocity at the same time.
Okay.
That's the problem. Well, it's not a problem. That's what we need to learn. The reason that we need to learn this one is because we need the mathematical description that allow us to sort of like how can I say it? Like put in these informations inside like a single line of equation or something. And that line of equation will have all the information about the waves and all the information about the movement of the medium or the hands. Okay, maybe this is like introduction is a little bit too long, but that's what it is. Okay, so this is what I have to emphasize you guys that this is what we are going to do today. And for those of you that sort of like learn this stuff back in like maybe high school or something, and if you feel like these topics over here sort of get very confusing, or I don't know, it's like why is somehow it's kind of like, you know, made mistakes all the time. There's something missing. There's, you know, that's because of what we're about to study today. I don't know, maybe that's part of the problem. But for those of you that haven't seen it, that's fine. Just dive into it, guys. Okay, here we go. Let me ask you a very simple question here. So somehow if I generate a wave, it doesn't have to be a continuous wave. I can just generate something we call a pulse. So if you look at this wave, you can imagine that what kind of hand has to move. Your hand's gonna move up and down, and that's it. You're done. Once you move your hand up and down, you're gonna generate a wave pulse that look like this, right? You guys make sense? Yeah, cool. And let's say somehow I have a way to describe this wave using f of x to describe this shape of the function. Perfect. Let's say I know how to write this one down. Okay.
Okay.
My question is this: what will happen to this wave at later time? Give me the expression to describe this wave at later time. Let's say I'm going to ask you, hey, what happened when this t equal to 5 seconds? What happened to this wave? Given that you know that the speed of wave is v, what will be the f of x form? I think I can say that. The form of the function that's describing this wave, this form. I want the wave at 5 seconds later. Okay, that's some contribution over here. Okay, all right, very good. This is very realistic. Okay, for some of your friends say it's getting smaller. That's for sure. But let's say if this is in like an ideal world, there's no friction, you're not losing any energy. So it means the form of the wave will keep fixed in this shape all the time. So it's just going to travel passing you from left to right. So I'm asking you the mathematical description that describing this wave 5 seconds later. How would you write that down? Whew. What do you think? All right. So this is the key. And to me, I think this is the pretty much like the most important stuff that if you understand this one, then eventually the business that we are going to do today is going to be quite all right. Let's see what I'm at here. I'm going to have to add a page here. And let's sort of like follow my logic here if you sort of okay with that. Here we go. All right. So I'm going to ask you a very sort of like familiar mathematics here. So if you have XY axis, and now think of it like you have a straight line, 45 degree. Everyone knows the equation to this one is just going to be y equal to x, correct? So far, so good. Now, if I have another line, or let's say I'm moving this line to the right by a distance a. So that means I'm going to hit this x-axis at a. What is the green line equation, guys? All right, I'll do it myself then. All right, y is going to be equal to x okay, any participation here? No, just, all right, x minus a. Does that make sense? Because it's still a straight line, the slope is still 45 degrees, or the coefficient in front of it is still 1. But then you say, okay, John, because you slide this line to the right, the y-intercept is going to be negative a. That's fine. Okay, cool. Now I'm doing another thing. Like, okay, John, instead of going to your right, I'm going to your left. And let's say I'm moving to B then. So the cut is at negative B. So what would be the blue line equation, guys? You guys just say, okay, then you're going to have the y-intercept at B. So the equation here will look like y equal to x plus b. All right, it's no big deal. This is like, okay, simple enough. So let me do this with another kind of function. So let me compare this with the parabolic curve, shall we? So if you start with parabolic curve, let's do a simple one, y equal to x squared. And then I'm going to translate this parabolic curve to the right by a distance a as well. What is going to be the green parabolic curve expression, guys? You guys still with me, right? I'm not talking to just the webcam, right? Very good. Okay, there's some sort of like participants over here. Oh, cool. Thank you. Thank you. All right, then. Okay. All right. Okay. Very good. Very good. Very good. Keep it coming. Very nice. Here we go. It turns out to be this. With me, guys? For those of you that sort of like think that, okay, could it be y equal to x squared plus a or minus a? You don't even, you have to squeeze the a inside the x. Otherwise, then all you're doing, you just shift this whole curve down by the distance a. Does that make sense?
Okay.
All right, just have to be careful right here. So this is the stuff that I want to revise with you guys, that you have to make sure that minus a actually is stick with the x. So it turns out to be that x minus a, the whole thing square. Cool. Very nice. Got that? So far, so good. Now I'm doing the same thing if I have parabolic curve that slide to my left instead. So what would be the blue curve over here? Now you start up like, okay, John, I think I know what to do, because now it's to your left. So this blue curve will look like x plus a squared. Cool?
Okay.
But there's nothing to it. Well, John, it's just it's sort of like, I think this story over here, you probably have heard it from, it's called like shifting the curve or something. When you have a curve and you want to slide horizontally, you slide to your right, then you put x into x minus the distance that you slide. And if you want to go the opposite way, you do x plus. And if you want to move up, you add that distance to the whole function. And if you want to move down, you subtract the distance to the whole function. Okay, does that sort of like, you know, bring back some memory a little bit here, right? But that's not what I want. What I want is this, guys. Okay, let's come back to my parabolic curve. Y equal to x squared, right? I want an animation.
Okay.
Can you give me an animation of this parabolic curve that is traveling to the right? I'm asking you this, guys. I want this to move. You know, imagine an animation, right? So this parabolic curve is just passing your face like this. I want an animation. Okay. Oh, thank you. Thank you. All right. I just want to check like you guys still, you know, with me or not. Sorry. B, thank you. Okay, my bad. Okay. Plus B. Thank you. Very good. All right, got that one. Thank you. Okay, so now imagine I have y and x equal to x squared parabolic curve just like before, but I want an animation, guys. I don't want like a static shift like this. I don't want like a, you know, just translate and I'm done. I want it to go like this. I don't know whether that makes sense or not. Like, I mean, do I have to go backward here? I don't know. But anyway, I want an animation. Okay. You probably ask me back, well, John, how fast you want this parabolic curve to move? Well, I say, okay, I'll give you the velocity of this wave, V, just like what we did. How are you going to do it? Okay, maybe too much now. Okay, the answer is very simple. So go back to our business over here, and then you say, every time you translate a curve to your right, you say you just do that negative A thing, right? But now, because you don't want a fixed amount of translation, you want an animation. So that means your translation supposed to include the time factor. Does that make sense?
Okay.
Yeah. So you want the factor that include time. Time will keep going up. You know, it never stop. It just keep going. So that means instead of giving you a fixed value of A, you say, give me a distance, guy. And everyone know the distance can be described as the velocity times time. See, I have a time factor built into this displacement, and time will continue at, I mean, it's a continuous change. So it's keep growing. So that means all I'm doing over here is, but Adan, that's easy. What you want to do is just plug in this and you do y equal to x minus vt, the whole thing square, and you are done.
Okay.
Easy enough, guys? So from now on, every time that you see x minus vt, in your head, it's like it's just x minus some distance that is going to get shifted or translated. But because the translation depends on time, so this one will show up as an animation in time. And that is how things gets moved. And that's what we want. We want the wave. The wave behaves just like this. It's just passing your face. And you come back here. Now, can you answer me now? Come back to this question, guys. What will be the function at time t? If you are given f of x as a function of time, as a function of this wave that you are seeing in the front. Yeah, the answer is, don't think too much, it's already in the slide. There, got that one now? So all I'm asking is you just change the f of x into f of x minus vt. And the vt will just give you the animation, how far away from the starting point that the waves is going to be at. And now if you want at 5 seconds, no problem with that. You just substitute 5 in here. And then you know exactly the shape of the curve at 5 seconds later. When they say later, what does it mean? It means you probably have this already with you, but you just set t to 0. That's why time doesn't show up in the original function. Does that make sense? Okay, all right. I made mistake again. What square? What square? Should it be square? Oh, never. Okay. Okay. All right. Got it. Okay. So over here, this f of x could be any kind of function. It could be exponential. It could be a polynomial. It could be logarithm. I don't care. The key is the form of the function. From now on, every time you see x minus vt, that is a wave. You are done.
Okay.
Seriously. All right. And I'll show you what it means by, give your conclusion, and then we'll attack some, examples. So from now on, every time that you have x minus vt form of the function, you can say right away, you have a wave that is traveling in the positive x direction, because you notice there is a negative sign right here. You know that the negative sign means everything translated to your right, right? Even that the right is positive x. And whatever the numbers shows up in front of t, that is going to be your velocity, or how fast that wave is traveling. On the other hand, if you have the positive x plus vt, then it's going to be the wave traveling in the negative x direction with the velocity v. Cool? All right. And now we're going to name this the wave function. Every time that you have a function that is in the form of x plus or minus vt, that is qualified to be waves. And then we're going to call those functions wave function. That makes sense, right?
Okay.
And every time that you can, you want to draw a wave on a paper, on a screen, capture it in whatever, or you put it on the textbook or whatever, you can see that this wave is not traveling. However, wave never stop moving. Waves have to move. All the waves gonna have to continuously move. It cannot be stopped. So the only way that you will be able to capture this thing is you just have to take a photo. Does that make sense?
Okay.
You have to take a snapshot. You freeze the time. The wave just keep moving, but then you just have to take a photo to stop freeze. So that's why every time you have a snapshot of the waves on the paper, on the textbook, on the screen over here, it means you have to freeze the time. So that means you just have to somehow pick a time, fixed t. Give me some time. You want it at t0, 1 second, 5 seconds, or whatever. But once you pick the time components in the function will just get replaced with a number. Does that make sense? So once that get replaced with a number, then all you left is going to be just a function of x because t has been replaced with number and you are dealing with a waveform. Isn't that cool? So from now on, every time you talk about the waveform, which is the form of the wave, the only way that you can look at the form of the wave is just by taking a snapshot. Freeze the time. Bam, you have to stop the time. You will look at it, and that is your waveform. Cool? Okay, so far so good? All right, if this is good, let's give it a practice, shall we? Okay. All right, so come back here. Here we go. Guys, try this one and see how it goes. Can you answer this question or not? Oh, okay, there's a question. All right, I'll answer that during the break, shall we? All right, okay. Oh, that's a very interesting question. All right, maybe we'll discuss toward just right before the break. That is a very good question. Yeah, okay. All right, guys. So at time 0, you have a transverse pulse in a wire that's described by the following function. And you don't even have to worry about plotting this curve or whatever. You can use like Google Mathematica or whatever to plot this one out. But the point is, write the function y of x and t that describes this pulse if it's traveling in the positive x direction with a speed 4.5 meter per second. Go ahead, guys. Actually, it's supposed to be, I cannot put some other music into this one. So what would be your question, your answer here? Whatever you're thinking is correct. I'm sure you guys sort of got this one. I'm sure. Here we go. So for sure, what are you writing is going to be a function of x and t. And it's going to be this, guys. Don't be afraid. That's it.
Okay.
I'm done. Simple enough. So from now on, you will be able to put any curve that you can write it as a function, mathematical function, f of x, into an animation all the time by just introducing that factor right here, vt. Done, guys. Super simple. But that's the point. The difficulty that sort of like creep in right now is this. You are automatically get into the area of two variables function. So there's no doubt why when you study these topics over here, the mathematics get complicated automatically. It's because you are suddenly talking about the two variable functions. And to me, it seems like, given that you talk about the high school physics, I think maybe this is the only topics that dealing with two variables function. I think so.
Wow.
I don't know, but yeah, it's pretty close. All right, guys, try again. Come on. You have a pulse moving along x-axis, and it's described by the following equation. You don't even have to care what shape of this one is. But even though for those of you that are familiar with statistics, this one is a bell-shaped curve. So it's like a what lakang kwam, yeah. So that's what you got it from, like a normal distribution and all this stuff. This is the shape of it. But anyway, for us, x is in meter, t is in seconds. Determine the direction of the wave motion and the speed of the pulse. Go ahead, guys.
Okay.
What is the direction? When you look at this, what John is positive sign between x and vt. So I can say right away it's going to be negative x direction, and it's done.
Okay.
Simple. Or you can call, I mean, for us, I think if you want to say travel to the left side, that will be fine because we pretty much usually take left to be negative x. All right. But I mean, negative x will be more general. What about the speed, guys? I'll do it. It's whatever numbers that show up in front of t. And the speed of pulse is just 5 meters per second. You are done.
Okay.
Okay. That's simple, guys. Don't think too much. But then what we want now, that's going to be something that we want to do next is this. Because you can pretty much come up with any form of the function and then you can put it in the translation, animation, and everything works fine. But then there is a particular type of waves that is so crucial in everything else that related to waves. And it turns out it's going to be a continuous wave. So it's mean it's going to be wave that keep, going, and going, never stop. And when you imagine that, go back to the original example over here. So if your hand that is holding that spring keep move up and down, you now see that you generate a waveform that associated with the motion, right? So whatever the signature that you get from the waves, it's going to actually link back what is the behavior of the movement of the source. Does that make sense? Okay, so the source of disturbance, your hands move up and down, do something. All those things that you do will pretty much get sort of like transfer. I don't know the word transfer is a good one, but at least it will get sort of like embedded inside the waves. So the shape of the wave depends on how you move your hands. So there's no doubt. If your hands behave in some very, very specific manner, you should have some mathematical description of waves that have that specific manner of the motion as well. And that's the reason why we studied simple harmonic last time. Because what if I am moving my hand in a simple harmonic motion? So this means it's going to be up and down in some frequency. So I have like a fixed frequency and move my hands up and down in a simple harmonic fashion. So you can guess that you eventually going to generate a wave that is also a sinusoidal wave going out in the continuous manner. Does that make sense to you? And this is a nice thing about the simple harmonic motion and the classification of waves. No matter your movement is transverse, which is that means your hands move up and down, or you want to do in the bottom case that your hands moving forward and back, you use the same mathematics because I don't care. It's simple harmonic motion. It's a sinusoidal, or you can pick cosine, doesn't matter. But it's a sine and cosine function. And I don't even have to worry about the direction of actual movements because you're going to use the same mathematics. Does that make sense?
Okay.
So that makes things so simple in the sense that once you understand this whole thing, it can be applied to both transverse or longitudinal waves. Doesn't matter. The form of the mathematics still the same. And we are going to focus on simple harmonic motion source. The source that actually perturb or disturb the medium in a simple harmonic fashion. Cool. So you can expect it's going to be sine and cosine function. So that's what we are going to do next, which is the sinusoidal waves. Does it sound reasonable, guys? Okay, this is good. So if this is good, then let me just start a quick look at this. How are you going to do this, guys? Okay, and it's going to be super, super easy because now we understand how it's done. So I'm going to start this and then we can pretty much finish everything after the break. Start with this. So you have, once again, let me draw. Okay. And everyone familiar with the sine and cosine. So let me pick sine then, because I think maybe that's the one that people familiar the most. Okay. So what I have is, let's say if I have a sine, and then we just allow me to do some, adjustment of the shape of this sine. So I put A in there, and everyone still remember this one is the amplitude, because that's how high this thing can go and how low this thing can go. So that's the A it's for. But then, because just to keep some flexibility, how can you squeeze in or extend it out? I put some factor in front of X. So when you adjust the K, that allow you to, squeeze in the shape of the sinusoidal wave, or you can stretch it out. So the reason that K is there is because, I wanted to have some factor that you can play with the shape of this one. Guys, make an animation for me. I want this wave. Again, this wave is actually continuous, right? So it's just keep going, never stop. All right. I want this to just, keep going and passing you by. Yeah. What will be the form of the function, the sinusoidal function, that represent a traveling wave with the speed v? Then let me give you the speed of the wave v. And yes, you're right. So if I want a traveling sinusoidal wave, what I'm getting is going to be, of course, two variable function. A sine, because it's traveling in the positive x direction. Let me call this x, right? So it's going to be k x minus vt. Everything is in this here, and you are done.
Okay.
Got that one? Is that, I don't know, is that too simple or not? But I think now you understand how it goes. If you want this wave to travel to your left, just turn that negative sign into positive sign, and you have a left traveling sinusoidal wave. Okay? So the business of wave is going to be super, super straightforward. And we're going to be able to, assign all the terminologies and everything once we analyze what we are having right here. But first thing that I want you to get is like a take-home message for the first half of the lecture is, now you know, every time that you have x minus vt, it's a wave. Okay? And we will continue on after the break, guys. Take 10. Okay, so what we are about to do next is just to see how can we extract stuff from what we just learned in the first half of the lecture. Sounds like fun, maybe. All right, so what we have over here is, when you look at this, so now you should understand what is actually going on now. Look at the orange curve over here. That's your starting point. So that could be what you're saying. This is at time equal to 0. Yeah, that's when you start. And then this orange curve is going to continuously moving to your right. Think of it like animation. It's a wave, so it's never stop. So it's just going to travel to your right. So the blue, that will be the ones of the orange at later time. Okay, make sense? Okay, so that's good. So now what we have over here is this. So when you look at this, now we are going to look at each parameter that we introduce in here one by one and see how can we extract the information about waves from just, mathematical description that we have in front of us right now. My first question is, guys, what is K? When you say like, what is K, is like the question is just so broad. So what does the K actually related to the structure of this sinusoidal wave? The good thing about the sinusoidal wave is it has like a continuous, change, and everything is just like the structure of this one is just periodic. So everything just repetitive, just going back and forth, back and forth, back and forth. So think about this. When you have the K factor in front of X over there, let me compare between this. If you have y equal to a sine x, and another one, let me call like 2, then a sine 2x. What's the difference between the two, guys? Well, then that's not bad. So if you have a sine, it's going to look like this, right? A sine. There you go. You just keep going. That's a y1. But then a sine 2x, it means it's going to accomplish everything that the sine x can do, but half the x. Does that make sense? Right? Because you need like half the x to accomplish whatever the y sub 1 can accomplish. So that means what you have over here is just like everything is going to be done just taking half the space. Does that make sense? All right, so that means the K factor right there, we just give you the squeezing factor. It's just like the bigger the K, the smaller your sinusoidal wave is going to get. Okay. So that's what the K is about. However, just to be able to communicate a little bit better. So let me ask you this. If you would like to measure the distance, here we go, come down here, between 2 points that look alike but adjacent to each other. So you look to the next one that look exactly the same, and then you call that distance the wavelength. With me, guys? The wavelength. So that is just the distance between two adjacent places that look exactly the same on the wave. That's the wavelength. Okay. So if you take that one in here, so that means whatever the wavelength that the red has, okay, the red will have the wavelength over here. That means the green will have half of that. So that is the clue that I'm trying to get to you. It's just saying that the K must be related to wavelength somehow. And we're going to use lambda to represent that wavelength. Okay, the lambda. Now, what is the relationship? It's pretty straightforward, guys. Look at this again, Kx. Now, every time that you have the sine Kx, everyone knows everything that comes behind sine will complete one cycle when those factors move by 2 pi. Does that make sense? So that means if you take this one and spin it 2 pi, that's when you complete one full round, one complete cycle. But then when you look at the wave, the whole thing will just come back to its original point. That is exactly one cycle. So that means you must have traveled yourself by a distance of one wavelength exactly. So that's why what I can say is K with the X at the lambda right here, right there, that will be equivalent to the angle of 2 pi as an argument in the sine function. And that's it, guys. So what I can conclude is K is just 2 pi over lambda, and you are done.
Okay.
Cool. So from now on, whenever you have a coefficient in front of that, that's still K. And once you know the K, you know the wavelength. Done. Let's conclude this slide over here. Nice. All right. But then that's not done yet. Let's continue on to our full animation over here. You have like Ajahn, you have like Kx minus Vt and stuff. So let's do one thing further, shall we? All right. So what we are going to do next is this. I'm going to manipulate this one down here just a bit and see how it goes. So what I'm going to do is, okay, let me sort of move this thing around a little bit. All right, I don't need that anymore. That's too much, yeah? All right. Okay, I just only need this part out. Okay. Okay, going away. There you go. All right, very good. All right, nice. I have to practice doing this kind of thing more. Okay. Okay, that one. Nope. All right. All right. You guys know, like, why don't I use iPad? Yeah. All right. Okay. It doesn't work. I don't know. Can I scale it? Oh yeah. I don't know. There's some problem with the interface here. It's not so smooth. All right, guys. So what I have over here is I'm going to manipulate this one a little bit further. Here, spread it out. Kx minus kvt. All right, so far so good. Next, that k thing, we just learned that can be written as 2 pi over lambda vt, correct? So far so good. Now, can you guess what should be going on next? You have to guess. Well, yeah, Dan, you can just move to the next slide and you're done. Yeah. No, that's not what it is. It's just like, what about the speed of waves? What kind of relationship that you can get from the speed of waves? So what do you think about it is this. So when you look at this curve down here, you define the lambda, you know the amplitude and everything. But do you notice something different here? It's not different, but you notice something that, Dan, it's written or it's plotting against x. But we just said the function that we are looking at is two variable function. It's x and t. So what is going on with the time? So you have to pick and choose. So over here, you pick the time. Remember the snapshot, take a photo. So the only way that you can draw this one out, have X as your horizontal axis, it means you take a photo of this curve. See, top figure, that's your animation. You take a photo at time equal to 0, you get the bottom figure. Perfect, right? So how can I get the wave that as a function of time instead? How do you do that, guys? Because you have two variables, right? So imagine this. If you are floating in the sea and there is an ocean wave passing you, the ocean wave just, come from wherever far away and then just passing you by. And you are floating. When you say you're floating, to you, you only move up and down. Does that make sense? The wave just keep passing you, but you just move up, down. Right? You're not surfing or anything, right? You're just surfing. You're just like, just floating, doing nothing. So your body is actually moving up and down in the sea, up and down. So you're saying that your position is fixed. You're not moving anywhere. Even though in reality, you're going to move forward and backward a little bit. But let's forget about that, possibility there. Let's say wave that's going through you allow you to do a transverse motion, right? You can only go up and down, but at a single position, X. So that's exactly what you should do. To do that, you just have to freeze the X. So you have to pick the X. Once you pick the X, X will turn into just a number. So your function will turn into f of t instead. Does that make sense to you guys? And that's the time that you're going to be able to plot your position as a function of time. You go up and down in time, up and down in time. So that's up and down shows up as this curve right here. See, be careful with the horizontal axis there. So now you still have the shape of the curve no matter what. No matter what you plot in X or you plot in time, you're going to have a sinusoidal characteristic. You cannot get away from it. But at least now you know the horizontal axis now is time. So if you're going to measure the distance between two lookalike that adjacent to each other, you're going to get some sort of distance, but it's not a distance in space anymore. It's the distance in time. And this one you already know what it is the period. Just like the period that you saw in simple harmonic motion or a circular motion. That is the time that it takes to complete one full cycle. Does that make sense? Okay, now we are dealing with in the time dimension over here. But the A is still the same amplitude because, you move up and down. That is your transverse motion. So the amplitude is your maximum displacement that you can do. That's all. So over here, you can now say the period is in here. And if you want the inverse of the period is still frequency, that is fine. But now the nice thing about knowing this period is this. Guys, how fast this wave travel in terms of the wavelength and the period. You guys said that that's easy because the speed is just distance over time. But now we know the wave will travel exactly one wavelength. Taking how long? Taking how long? Of course, one period of time. And then you can flip-flop that thing. You can call that period to be inverse of frequency. And that's how you get this equation right here. V equal to F lambda. You probably have seen this equation before. But this equation is nothing more than just distance over time. But you write it in terms of the parameter that we're going to use to describe waves. Okay, so now from now on, I hope that every time you see V equal to F lambda is nothing like super duper like amazing or anything. It's just like distance over time. And then you just write down time to be just, time to be just frequency. Cool. All right. So now once you have this, come back to our business over here. So about V equal to F lambda. So that means I can manipulate this one more step further. Kx minus 2 pi over lambda. V equal to F lambda. Nice. Now you can cancel some stuff here. And does it look sort of like familiar to you guys now? Whoa, 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 whoa. You have the 2 pi f. What is 2 pi f? Yeah, is the angular frequency. just like what you did in the circular motion, just like what you did, whatever you had done before. So that means now I can re-express this one in a very compact form. It's a kx minus omega t. And that's it, your sinusoidal wave function. So I hope by showing you how to do the animation, and then you know, sort of like put in the sinusoidal waves and make it animated. So you have a sinusoidal waves function. And within that, you can read everything out of it. So now by just looking at it, you know the amplitude, you know the wavelength that's hidden inside the K, you know the frequency that's hidden inside the K and inside the omega. You know the wavelength, you know the frequency, you can say V equal to F lambda. So everything about the wave is on the right-hand side of this equation, and you are done.
Okay.
Isn't that cool? It seemed to me that is pretty much like that's amazing, because that's cool. That is just like, okay, it's like just one line of equation, but that gives you all the characteristics of the wave. That's so nice. Okay. And of course, if you look back at this in the textbook, in the slide, there's some derivation of stuff, and I think that's maybe too complicated. I have already concluded for you guys. So that is it, guys. At the end, you know what the K is. You know how to figure out the velocity. You know the angular frequency. You can pick and choose the form of the wave equation that you like. And from now on, if you read the textbook, you don't have to worry. They are all meaning the same thing. It could look like the first equation over here. Nice. You see x minus vt, that is your animation all the time. Any function that has an x minus vt form must be a wave. Or you might see kx minus omega t. That is fine. I know what the k is. I know what the omega is. I don't have the problem. Or some textbook just sort of split it out, write everything, you know, spread it out, write k as 2 pi over lambda, write omega as 2 pi over period, and then they just pair things together. They sort of like pull out the common factor 2 pi, and then you just write x over lambda in one term, t over period another term, and that's the same thing. That extra phi naught, this is freestyle. This is up to you. You can always add that constant, the initial phase constant, up to you. Initial phase constant, I think it mixed the two terms together. Sorry. You can add the phase constant, or you can name it like an initial phase factor into it, whatever, whenever you like. That's the phi naught that is there. But the nice thing about this ratio in green over here, I think some physicists or some other like this one, because it gives you a sense of what is going on in both space and time. You sort of see what this is trying to say. This gives you a ratio of the distance that the wave travel relative to the lambda. And every time that you know that whenever you move one complete lambda, you turn your angle by 2 pi. That's that kind of like beautiful here. So this term just saying that if you travel in space by the x distance, how can you convert that distance into angle? Same thing with time. So you say, okay, I know that it would take one period of time for the wave to cycle through one complete cycle. But then because you travel, you wait for t. So what is a fraction of t relative to the period? And then you just convert that into angle by multiply by 2 pi. So this last equation has like a nice symmetric way of representing the space and time factors in the waves equation. All right, but to us, now they're all the same. It's just trying to engrave all the information about the waves on the right-hand side of this equation. Sounds good, guys?
Okay.
It's like something that's kind of like straightforward here. Okay, so if that is the case, everything about waves now can be read from this expression. Okay, so and I can that out now, so you know how to do it. Let's practice, shall we? So now you have an ocean waves with a crest to crest distance of 10 meters. It can be described by the following equation. Answer everything here. What is the wave number, the velocity, the omega, and what is going on at time 0 and times 2? See, can you read it now? So start by looking at this, Ajan. That is x minus vt. Whoa, nice. Okay, so with that, whatever come in the front, that is your k. So what I can say is just say, all right, k is 0.63 and I'm done. Very good.
Okay.
Simple as that. What is the speed, guys? What is the velocity of waves? Don't need to do anything. All you need to do is just read. Here we go. Whatever the factor that come in front of t, that is, in this case, it's x minus vt form. So that means the v is going to be 1.2 meter per second. Everything is in SI system. And what about omega? Now, the omega that's now up to you. If you want to go straightforwardly, what you can do is this. Well, Ajan, I'm going to just distribute that factor in 0.63x minus 0.63 times 1.2t. And we just said, whatever comes in front of t in the kx minus omega t factor here, that is going to be your omega. With me, guys?
Okay.
So what I'm saying over here is now you can pinpoint your omega to be 0.63 times 1.2 and you are done.
Okay.
Is that too simple? Maybe not, all right? But at least now you sort of like, okay, have a way to go around this thing and then extract information out. Another way that you can approach the omega and all this stuff is this. If you look at the expression of the F equal to, V equal to F lambda, and now you sort of like, Ajahn, there's so many things going on with the 2 pi f, 2 pi omega, on and on. So what I can do is I just multiply and divide out the 2 pi. I haven't done anything, it's just exactly the same. And then what you can notice is over here, 2 pi f is omega. Yeah. And then you say, Ajahn, 2 pi over lambda, that is going to be UK. So that means another expression for the speed of wave can be written like this as well, is the omega over k. Cool. So actually, to figure out the omega, you can also do equally well by just taking the k multiplied by the v. The k come from the part A, the v come from part 2. So you can do the k times v as well. It will work exactly the same. 0.63 times 1.2. Cool?
Okay.
All right. Now, part D and part E is going to be just simple plug and play. But what you get at the end is all you get in part D, you're going to get y, x, 0. See that? So you're taking a photo at t0. So you're going to end up with a wave form. Part E will be exactly the same, except you just substitute t equal to 2. You take another photo. When you wait 2 seconds later, you get another waveform, right? Don't worry, in the exam or whatever, I'm not going to ask you to sketch anything because nowadays you can sketch it online or whatever, all right? But that's at least the thing that you need to understand is waves is 2 variable function all the time. That's the thing.
Okay.
All right. And I'm not so sure about this. Maybe this is my mistake over here. I just say the distance from crest to crest is 10 meters. So that means lambda is 10, but I'm not so sure. Is it going to be exactly the same as 2 pi over 0.63 or not? You have to check for me. It could be like over informed and that information turns out to be a mistake. So, right, we don't need that actually. So I can just erase that first line. I don't know why it's there. Maybe just confused. All right. But anyway, just by having the equation, you should be able to extract all the information about the waves at any time. Okay, try again just to make sure that you got what we are looking at this point. Okay. Oh, okay. Right before we jump right into the next example, right? I thought we are gonna do that after. Sorry, just confused the steps a little bit. So what we got so far, now you know how to read everything, right? About waves by just sticking with what you just look at just only the right side of the equation, right? A, okay, K, omega, the V, everything is here. All good. Now you have to go back to the origin where you started out. It was trying to get to the source, right? The source is the one that start everything. and that source disturbs something, and then disturbance get propagated as waves. So look at the right side over here. See, this is the scenario that we started out. You have a rope, and the end of the string is attached to a blade. This is the example that they use in the textbook. And now you set the blade in motion. So it's just going to flip up and down, and it's oscillating. So that is your disturbance going on. And then if you set this blade to oscillate in a simple harmonic motion, you will generate a sinusoidal wave out. So now you got it. Good. Okay. And the amplitude, the wavelength, the omega, everything is done. Now, let's pay attention to a single point on this string. Once again, imagine back in the example that I'm talking about, that you are floating in the sea. The only thing that you travel is you're going up and down. You cannot ride the wave. You're not surfing or anything. So you cannot go along with the wave. You just go up and down, up and down. And that up and down will give you where you are in the vertical direction. See, if you look at the blue, now you go up, back down here. Now you go down, and then the whole process will just continue again. Yeah, this is, I don't know what is going on. Just doesn't want to take mine. There you go. It's bug in the software or something. Here we go. All right, so what you have over here is, see, look at the P, the blue point over here. You start there, okay? And then you go up there, and then come back, original point, go down, and then you repeat the whole thing. You sort of like look down, look up, look down, look up, on and on like this. So you only travel in the vertical direction. So the whole function that we have been studying, once you plug in the X and T, right? Because you have to specify where this X is, and you have to specify when you want to take a photo. Once you, bam, pick X and T, you substitute everything into this expression over here, bam, X, bam, T, everything now will come out as a number. That number is the Y on the left of the equation. What is this? This is here, Y. How far away from you, from the equilibrium point you are in the vertical direction, if we are looking at the transverse wave. But if this is a longitudinal wave, it's going to be the same thing. So the whole right-hand side of this equation will tell you where you are. Make sense with me, guys? All right. So, I mean, if we are looking at the transverse wave, it will tell you how high you are relative to the equilibrium point, which we take it as 0. So that is the Y displacement. Got it?
Okay.
Cool. So that means you can guess, if you have a displacement in a sinusoidal wave, that is your simple harmonic motion automatically, right? Yeah. So if you want the velocity, you did this before. All you need to do, you just take the derivative of this displacement with respect to time, and you will get the velocity. We put the subscript Y just to signify that this is a transverse velocity, to distinguish this with this wave speed. There are different speeds, right? Not the same. So this is the speed of the element in the medium that actually going up and down, up and down, up and down, because the derivative has to be done just only with the t variable. You don't have to deal with the x. So that's why it's a partial derivative here. But it's a simple derivative because you take x as just a number. So what you do is just you take derivative of this. A is there. Okay, sine, you get cosine. Don't forget the chain rule. You have to differentiate whatever inside, you get extra minus omega out. That's the chain rule. Isn't that cool? And once you have that, then you understand that whatever come in front of sine cosine, that will be the maximum possible value. Yeah.
Okay.
So if that is the case, just like what we got in simple harmonic motion, that is your maximum speed. But this speed is your transverse speed, yeah? Not the wave speed anymore. Speed that you travel up and down. It's not going to be a constant. It's very easy to spot. Wave's speed always constant, but the transverse speed is simple harmonic. You have sine and cosine function. If you want acceleration, no problem, Ajan. You just do it one more time. Take this velocity, differentiate with respect to time. Okay, so it's going to be partial derivative again. Treat x as just a number. You do the derivative of that cosine, you get negative sine. You have that extra negative omega out. So the negative cancel, you get extra omega. So at the end, you get omega square factor times the a in front of the sine kx minus omega t. So the acceleration has to simple harmonic. You saw that before. Okay, and this is going to give you the maximum possible value as well. So omega square a is going to be your maximum acceleration. Isn't that cool? All right. And once you understand this whole, scenario over here, and I hope by now you will see the close connection between the simple harmonic oscillations that we studied last time and the wave generation that we are seeing right now. See, it has to be because sinusoidal waves in the simple harmonic is the source of disturbance and is going to generate the same kind of characteristics, which is the sinusoidal waves. So think backward. If you are seeing a wave that move in a sinusoidal fashion, you will know right away the source must be simple harmonic motion. Isn't that cool?
Okay.
I don't know what's cool or not, but it's cool for me. All right. And there is a good sort of like I wouldn't say a formula, but it's like a shortcut somehow, because when you look at this, you have the space is already in the sine function and the displacement. The displacement is already in the sinusoidal function. And then when you do the derivative, the velocity is in the cosine. When you say sine and cosine, that is a sort of like a thing that you can apply, which is sine square plus cosine square is equal to 1, right? So that means you will be able to manipulate this and then get to using the sine square, whatever, plus cosine square, whatever, it will always equal to 1. So that means you just square the displacement function that you just saw. So it's going to be a square sine square. And then you square the velocity there, you're going to get omega square, a square, cosine square. And that's it. If you just keep this sine square term and the cosine square term, move everything to your left and just add them together into 1, then you can eliminate that crazy kx minus omega t altogether. So this gives you a very quick sort of nice connections between the position and the speed of the medium that is actually oscillating. Does that make sense to you guys?
Okay.
Is that cool? So let's practice this one a little bit. It's kind of nice to have, all right? Even though you don't need to memorize things, but I think this is very good. So think about this. It's a simple harmonic motion, right? So when you have a simple harmonic, okay, let me use this one. I hope it's easy to see. And in the middle of the screen, that's my equilibrium point. So when you do a simple harmonic motion, it's gonna go up, and then down, back in, boom, down to the bottom, and then go up again, boom, up top, boom, down, bottom, and boom, top. So at the peak, either the top of the screen or the bottom of the screen, the speed of this oscillation must be 0. We saw that's from simple harmonic motion. See? So that means try this. When you plug y to be a, your v sub y is omega square root a square minus a square, and that is 0. Does that make sense? So this expression is trying to see that, okay, all you need to plug in is just where you are. If you are at the amplitude, either positive amplitude A or the negative A, you're going to get 0 speed because that is your turning point in the simple harmonic motion. Isn't that cool? And of course, if you say what happens when y equal to 0, you plug it in, it's going to be omega square a square under square root. So it's omega a. And the omega a you just saw, that is your maximum vertical or transverse speed. And it happens when y equal to 0. So this means every time that you're passing your equilibrium point, that would be the fastest moving position there. It's just boom, and then just slow down, stop, and then just go boom, and then go down and stop at the peak, boom. See, so it's gonna move quickest, or the speed is the highest at y equal to 0 or at equilibrium point. Does that make sense? So this expression right here just give you a very quick connections between the speed of the oscillation and the position, and then you bypass that kx minus omega t. You don't have to, you don't have to know everything else because it's always like this.
Okay.
Cool. All right. Just in case you hit with some problems that you have to figure out the speed by knowing the displacement. So just remind you that there is like a shortcut. But if you don't have, then you just, okay, I'm going to go through sine square and cosine square equal to 1, and then you just eliminate kx minus omega t. That can be done as well. All right. But this is kind of like convenience to have this in the back. It's like a tool. Then you can, just pick it out and use it right away. All right, guys. So sort of like get what the business we are doing today, sort of. All right, guys, let's attack a couple of problems, shall we? All right, and then let's do 2. And then I think, was that 2 or 3? Yeah, I think 2 is good. All right, just do 2 and then we're done for the day. Sounds good? Alrighty. All right, guys, try the first one and see if you sort of get everything down and sort of like, I know how to do this. The string in the previous slide, the tip of the blade moving there, generate a wave, is driven at a frequency of 5 hertz. All right, good. That's F. The amplitude of the motion is 12 centimeter. That's good. So that will be your A, and then you can write it as like in meter. So it's 0.12. The wave speed is given, nice. That is your V, and that is 20 meter per second. Determine the angular frequency, the wave number, and write the expression for the wave function. Go ahead, guys. That's annoying, right? But that's just to wake you up a little bit here. All right, guys, let's attack angular frequency first. That seems to be the easiest one. It's 2 pi f. So it's going to be 2 pi times 5 hertz, and that is 10 pi. You are done. That's it, guys. The unit can be written in a radian per second. Oh, I don't need the bracket there. Cool. That's one down. Wave number, K is 2 pi over lambda. But then, John, I don't have the lambda. That is fine. You get the speed already. So remember V equal to F lambda, and it's omega over K. So that means you can figure out K by taking the ratio between the omega over V if you want, which is perfectly fine. Or you can use V equal to F lambda, and then once you get the lambda, you put it there and then divide it out the 2 pi, you get the K as well. Up to you. All right. So same thing. At the end, you're going to get the same result. You already found out that the omega is 10 pi. The speed of the wave is 20. So that is X pi and a half. What's going on with my pen here? That's going to be pi over 2. And the unit of the wave number is going to be 1 over meter. Of course, because it's 2 pi over wavelength. Cool. All right. Write down an expression for the wave function, guys. Woohoo. So you say y of x and t, 2 variables. Got to be the amplitude, 0.12 meter. You can pick sine or cosine, doesn't matter, same thing. I don't care because they don't specify when, where you want to start the wave, just want a wave. So that's fine, pick one. And then kx, pi over 2x. Yeah, you got k from here. Because they don't even specify which direction this wave is supposed to travel. And so they just give just a default option that the wave is traveling in the positive x direction. You can put negative sign there. But you can also put a positive sign, it doesn't matter. Kx minus plus omega t. Omega is already known as 10 pi. 10 pi t. You are done. Woohoo.
Okay.
Isn't that cool? All right. And for some of you, Rajan, if I want to add some extra fine, that's fine. That's your choice. That's no big deal. But because it doesn't even specify and is, there's no specifics here. So you can just ignore those and set it to 0. Just make it easy. All right, it's kind of okay. I think it's not bad. Yeah, the way that we can pretty much do this kind of thing is just like, okay, that's very doable. It's kind of nice. So far so good. All right, guys, one more just to double check that you guys happy with this. So a transverse wave on a string is described by the following wave function. Determine the transverse speed as a relation at particular time, at particular spot. That's okay. And part B, what are the wavelength, period, and speed of propagation of these waves? Go ahead, guys. All right, I'll do it for you. I know. Actually, part B seems to be, I mean, we should answer part B first. Yeah, I don't know why I put A first, but it doesn't matter. They're all the same anyway. All right. So we can do part B first if that feel like that's sort of like continuous from what we got from the previous exercise. What is the wavelength, guys? All right, you should be able to read this one now. I hope that's kind of fun. Whatever in front of X, that's the K here. See? So that means now you know right away the K is pi over 8. And K is 2 pi over lambda. So that means the lambda is going to be 16 meter. You are done.
Okay.
Cool. Next, what about the period? Whatever comes in front of time in the kx minus plus omega t form is going to be omega. So that's good. So what you have over here is omega is 4 pi. And omega is just 2 pi over period. So that means your period is just 2 pi over 4 pi, and that's 0.5 second. Done.
Okay.
And once you have the lambda, once you have the period, you can figure out the speed of the wave is just f lambda, or is just going to be lambda over period. You plug in the 16 from the lambda that you just got, plug in the 0.5 second for the period, 32 meter per second will be your speed of wave.
Okay.
See, you are pretty much like know everything. You can figure out the amplitude is going to be here. That's going to be amplitude. Yeah. And if you want, you're going to know that the direction of movement is going to be negative x direction, traveling direction. So you can extract all the information about waves by looking at the right side of the equation. Yeah, just the right-hand side, you're done. Now go back to part A, shall we? So for part A, determine the transverse speed. The transverse speed, let me put subscript y just to distinguish with just a regular v, is going to be the derivative of the y with respect to time. And you don't care about the x because you want to take the derivative with respect to time. And it's going to be 0.12, it stays there. All right, let me omit the unit, save some space here. Derivative of sine, you get cosine. Everything stays, no change. And don't forget the chain rule. So you have to do the chain rule. You have to differentiate whatever inside that bracket with respect to time. With me, guys? Okay, and when you do the derivative with respect to time, you treat x as a number. So the derivative of fixed number is just gone. The only thing left for you here is just the derivative of 4 pi t. So you're going to get extra 4 pi out here. Does that make sense? Yeah, let me write on top, save some space here. So the whole thing over here will give you 4 pi. So in conclusion, the speed of waves, the speed of the transverse speed is going to be cosine with the extra 4 pi. So let me put that 4 pi in the front. So make it nice and clean. 4 pi 0.12, and then the rest stays there. You are done for the transverse
Okay.
speed, transverse velocity. Yeah. So got that one, and it looks pretty good because it has to be like this. Because you saw it, it has to be omega a, at least. All right. But the negative positive sign depends on the function that you start with. But at least you have that omega factor coming out in the speed expression. So units, good. Let's do one more, the acceleration, shall we? So what about the acceleration? You do the derivative of the velocity with respect to time one more time. Go ahead, differentiate whatever you have up here. So 4 pi stays there, 0.12 stays there. Derivative of cosine, you get negative sine. With me? Everything's still there, no change. But then you have to do the chain rule one more time. Don't forget that. Cool. But it's the same chain. You get extra 4 pi coming out of this again. Cool, that's fine. So that go to the front. So at the end, the transverse acceleration is going to be negative is there. 4 pi square times amplitude sine pi over 8x plus 4 pi t, and you are done.
Okay.
Not bad, you think? I hope. All right, guys. Any questions? Oh, cool. All right. No question, seems like. So you guys sort of get this. All right, guys. So I think that is a good place to stop. And I hope that you learned something about waves today, especially the mathematical description of waves, plus the transverse oscillation. That sort of links you back to simple harmonic motion that we studied last time. Cool. All right, guys. Take good care of yourself, and I'll see you guys on Wednesday. Okay. Bye-bye.
Okay.